So I've started recording, so this is a weekly series on AI under the auspices of ICIP and C6 series. And I'm going to hand over to Francois Luus from IBM Research, who's going to introduce himself and speak about cognitive-assisted interactive labeling.
Thank you very much. Just going to move some windows around. Okay, yes, thank you very much. Hi everybody, my name is Francois Luus. I am from IBM Research Africa, in the South Africa lab.
AT&T's teleconference service. Please enter your network code followed by the #9. Para escuchar las opciones en español.
I'm going to talk about cognitive-assisted interactive labeling. So you might wonder why, if we look at the 4 sections of my talk, the first 2 are about radio frequency interference and radio astronomy, but it's going to become clear to you as the talk progresses. I'm going to talk about the discovery process that we went through in some of the work that we have done in radio astronomy in the South Africa lab. And then I'm going to build up to the implementation of cognitive-assisted interactive labeling that we have made. So in the first part of the talk, I'm going to talk about SETI RFI signal classification. So SETI stands for the Search for Extraterrestrial Intelligence. RFI stands for Radio Frequency Interference. And here we collaborated with the SETI Institute in the US. And in this picture, you can see the radio telescope that they commandeered. It's called the Allen Telescope Array. And it has about 40 dishes. So it's quite a formidable radio telescope in its own right. And it is exclusively being used for the search for extraterrestrial intelligence. So we tried to see what sort of big data analytics and machine learning solutions can we provide through IBM Cloud for the SETI Institute. And one of the biggest problems that the SETI Institute had, or opportunities I should say, is being able to prioritize follow-up measurements. So they have to triage or prioritize where in the sky they have to look next. So they want to follow up the most promising areas of the sky based on previous measurements that have been made. Now, the big problem with radio astronomy across the board, even for scientific radio astronomy, is something called radio frequency interference, or RFI. And that is man-made signals that are detected in the radio telescope. So the reason the South Africa lab is working in radio astronomy space is because of the square kilometer array that is being built. The core of the square kilometer array is being built in South Africa. So there's a big local effort to develop the SKA, which the first phase is yet to be rolled out. And to give you an idea of how sensitive these instruments are, we're able to detect airport radar signals from thousands of kilometers away in just 7 dishes currently up and running in the SKA radio telescope. So most of the time when you detect something, it is most probably RFI. If it's not, and it's a genuine SETI signal, then we would want to be able to detect that signal. And we hypothesized that these signals would somehow look anomalous. They would somehow stand out. Now, the big problem is that where the SETI Institute has millions of these signals previously recorded in their archive, they do not have any labels for these detected signals. So the task is, let us find the common classes of man-made RFI by looking at the spectral content of these signals. So in this image, you can see a waterfall plot where on the one axis you have time and on the x-axis you have frequency. And what this shows you is how the frequency content changes over time. So this characterizes the signal, and each type of RFI has a certain characteristic. And there are very common classes of RFIs. So now the big problem that we have is that we have no labels, and we have a very huge data set. So how do we initiate the process of machine learning? We want to be able to leverage machine learning to build a classifier so that we can say, okay, this signal is common, this signal is common, but this signal looks anomalous. So we first need to take out the common classes, and then we need to look at what remains to find the anomalies. So just to give you an idea of the diversity of patterns that can be seen in these little spectrograms, we have a 10 by 10 grid of little spectrograms. And it shows you different variations. So in the first column, we can see a typical narrowband signal. We can see in the third column here, we can see a little bit of a broadband signal. So there are common types of RFI that come out if you look across the data. And this is another approximately 10 by 10 grid of little spectrograms. So looking at the data, there is common patterns that can be seen. There are common classes of RFI, and we want to initiate the machine learning process where we have no labels. So that is the problem that we face. So we're gonna, in the next section, we're gonna build up to this result that you can see here. So notice as the cursor moves across each one of those little clusters that you can see a repetitive pattern in each one of the little spectrograms that are shown on the left-hand side. So using no labels, we can use unsupervised machine learning to reach this particular result, which it's fairly good. So what we're going to do in the last section of this talk is to see how can we use this as inspiration to greatly increase the efficiency of labeling itself once you want to start actually annotating some of these clusters that we can see. So in the next part of the talk, we are going to try and reproduce this result that we just saw. So this section is to give you an idea of the difficulties that we face if we have no labels, so as to motivate the tool that we have built that allows you to label large data sets with great ease. So the process that we're going to follow is shown in this flow diagram that we have here. So we're first going to try and extract some preliminary features, and then to take that 14 million number of samples and to reduce it down so that we can visualize compactly our feature space, where we have a representative sample of spectrograms, we need to execute the step of density equalization. Now, the big problem in this 10 by 10 grid of spectrograms, you do not see much because most of the data is actually noise. So one could use a variety of different methods to try and remove that 95% noise class before one continues the process. And the approach that we used is to say, okay, we need some features to start off with, some features that can give us a lower dimensional space where we can impose a histogram, as it were. So think about a multi-dimensional histogram that you place over all of the samples that you have, and where you might have multiple samples in a bin of the histogram, you're only going to take one. You're going to extract one of the samples, which are going to become the representative sample for that point. So you equalize the density and you get a representative sample. So the features that we extract are basic statistical features in this particular case. Across the two axes, time and frequency, we take statistical moments like the mean and the standard deviation, the skewness, and then we perform a principal component analysis, which just reduces the dimensionality. Then we equalize the density, and this 10 by 10 grid of little spectrograms shows you a cross-section, a sample that we can continue to work with. Now, another way to do this is to lightly engineer some features. So we can look at what is called the Fourier transform of the spectrogram. And that basically allows for patterns to be, pattern commonalities to be found independent of where in the frequency or time it occurs. And that gives us the following cross-section of little spectrograms. So this looks a little bit richer to me than the previous one where we just used statistical features. So now that we have reduced the data set where we have a representative sample, there are commonalities, but there's rich patterns, we can try and employ some unsupervised machine learning. And what we employ here is a method called autoencoding. So what autoencoding does is it's a type of self-supervised machine learning. So all you're trying to do is to take that input spectrogram and you're trying to recreate it. But what you're doing is you're compressing the waste of this model that you have. So you have to compress the data before reconstructing it. And that compression forces what is essentially a neural network in this particular case. It forces the neural network to learn a set of stencils. So you can think of it as a dictionary of patterns. A dictionary of common patterns needs to be found by this neural network. And then one can describe any one sample in terms of these collected patterns. So you're forcing the network to learn commonalities or good features. So you can try and get fancy, and there's different variants of autoencoding. So in these 4 columns, we can see dense autoencoding, convolutional autoencoding, and variational versions of those. And the important thing to note here is that one can use convolutions as opposed to fully connected neural networks, where convolutions help you to capture a very prominent property of real-world data, and that is the fact that you have spatial coherence in patterns that are observed. So if you have one hot pixel, you expect the neighboring pixels to also be hot. So you can capture patterns that are more true to how they appear in the real world. And so what we do here is, as you go down these rows, we increase the capacity of that waste. And that makes the problem a little bit easier for the autoencoder. So in the very first row, we have the original input spectrogram, and then we try and do the reconstructions from 3 dimensions up to, I think, 10 dimensions in the last row. And you can see it becomes more accurate as you add capacity in the waste. So autoencoding allows you to reduce your dimensionality so that you can basically inspect your feature space so that you can assist in the labeling process. That's one way to do it with autoencoding. The other way that we can do it is to take our lightly engineered Fourier features that I've talked about before, and we can use a method called stochastic neighborhood embedding. So what is stochastic neighborhood embedding? So stochastic neighborhood embedding is the main algorithm that we base our cognitive assistance on, that you'll see in the later sections. So stochastic neighborhood embedding is basically this idea that you can have a very high dimensional input space. So think about pixel level inputs that is fed into the system, and you have between samples, if you take 2 spectrograms and you compare them to one another, you can find some similarity. And most dimensionality reduction algorithms use a distance measure to obtain that similarity. And what stochastic neighborhood embedding does is it has a low dimensional space, which it's forcing all of the points into a low dimensional space. So typically 2D or 3D, so that you can visualize it to the human. And you're trying to recreate the high dimensional similarities in low dimensional space. So the T in front of TSNE is a special variant of stochastic neighborhood embedding, but this all started out in 2002. Plain stochastic neighborhood embedding was published, and here we can see for a very basic data set, it does a fairly okay job in being able to discriminate between the different classes in 2 dimensions. But there's a problem. If the complexity of the data set increases, you want to have better separation between the classes, which we don't have here. So in the slide, we can see the T-distributed version of stochastic neighborhood embedding, where you can see for that same previous data set, you can see a much better separation between the classes, and a change in this variant of stochastic neighborhood embedding that we're gonna talk about. And so dimensionality reduction algorithms basically started out by trying to recreate your dissimilarities or distances in the high dimensional space, recreate that in the low dimensional space. So that is multi-dimensional scaling. Then they said, okay, maybe it's going to be better to rather look at local neighborhoods. And with local linear embedding, that is what is being done. Look at only the local neighborhoods and try and reconstruct those distances. And then stochastic neighborhood embedding says, let's look at it in terms of similarities and trying to reconstruct the similarities as if they were probabilities. And then there were several improvements on the stochastic neighborhood embedding algorithm, and the most notable one is the introduction of a heavy tail or a fat Gaussian distribution. So normally stochastic neighborhood embedding would have used this taller distribution here, which is a normal distribution. But what the t-distributed stochastic neighborhood embedding does is it fattens the tails, and that allows you to recreate your similarities even though you're placing points a little further away. So the way that you can look at it in terms of trying to satisfy objectives, on the left-hand side you have stochastic neighborhood embedding. On the right-hand side you have t-distributed stochastic neighborhood embedding, and this big green patch that you can see here on the right-hand side, that is a value of 0. So no gradient is being applied to points that fall into that distance relationship. So that means that it's easier to satisfy your constraints with t-distributed stochastic neighborhood embedding. So it performs very well. So the big goal, of course, is to reproduce similarities, and stochastic neighborhood embedding says, okay, your pairwise similarities are effectively probability distributions, and we're just trying to minimize the discrepancy between the high dimensional and the low dimensional probability distributions. So the effect of this is, if you employ stochastic neighborhood embedding, for example, on our Fourier features, that is our lightly engineered features describing our spectrograms, you can see this histogram of pairwise similarities. And if you look at the x-axis, you can see a range from 0 to 15, 15 and 20. On the right-hand side, we have executed stochastic neighborhood embedding on this input data. And here on the x-axis, you can see multiple orders of magnitude going from 0 up to 0.5, but you see a crowding against the 0 axis. So that tells us that the stochastic neighborhood embedding has much richer similarity relationships. So it's probably going to be easier to be able to define clusters in this space. So if we take our data set of SETI spectrograms and we do a stochastic neighborhood embedding of those, in 2 dimensions, typically you have this spherical type of plot, and the clusters are typically string-like. And as you could see in the previous 3D version of this, there are similarities, there are expected to be similarities in each one of these separated little clusters that we have there. So one can address the curse of dimensionality. Basically, that is the fact that if you have a very high volume, high dimensional input space, your samples start to look equally similar or dissimilar. And you're not able to use distance measures to perform machine learning. That's why you need to reduce the dimensionality. So now that we've reduced the dimensionality, we can employ some unsupervised clustering algorithms, and all that does is it looks at separated clusters and it differentiates between them algorithmically. And so you can separate between clusters, and now conceivably you could say, instead of labeling one single point at a time, you can take one of these clusters and label the entire cluster with whatever RFI class you want to attribute. So that would be one way to achieve arguably cognitive-assisted labeling, although it's not interactive yet. So that is what we need to achieve. And then one can even have unsupervised methods tell us what's the optimal number of clusters. And then as you saw before, each one of these columns here represents the content of each one of those clusters that we can find. And then again, we get this result for a 3D stochastic neighborhood embedding. We get this good result where we had no labels to start this process off. We did a little bit of feature engineering. But overall, in retrospect, there is actually a lot of supervision that goes into this whole process, because you need to have the domain expert guide the process so that you can look at the correct features for the specific data that you're working with. So even in unsupervised learning, there's actually a lot of supervision that goes into the process. And that brings us to this idea of software 2.0. So now we have seen in radio astronomy especially, there is a huge need and a requirement for machine learning and artificial intelligence tools that can help the astronomer to explore the data and label the data. And with software 2.0, we have this idea of programs that can write themselves. So about a month ago, the director of AI at Tesla gave this talk at a conference. His name is Andrej Karpathy, and he talked about software 2.0 in their operations. And if you think about Tesla, they are operating the world's largest fleet of robots, and they're trying to achieve autonomous driving. And the striking thing about their approach is that they are almost exclusively using only labeled images to build their automated AI for automated driving. So they are trying to achieve this idea of software 2.0 in their production environment. So software 2.0 is basically this idea that you can, instead of hard coding an algorithm as you would do in software 1.0, you can have the program optimize itself. So the idea is not to replace software 1.0, but to have the two side by side, because you're always still going to have software 1.0 infrastructure that feeds into software 2.0. So some of the definitions that we have of software 2.0 is the fact that you are going from optimizing your hyperparameters as you would normally do in deep learning to only providing supervision. And this powerful statement is being made that in the future, data labelers are going to be the programmers. So the people that provide the labeled data, they are going to be able to build software 2.0 solutions. And one notable example of a software 2.0 model or skeleton is this paper, One Model to Learn Them All. They have built a model that you have to do no hyperparameter optimization, and this model can do image classification, it can do speech recognition, it can do language translation, just depending on the data that you feed into the model. So it's sort of like a one-size-fits-all model that just depending on the data that you give it, the supervised labeled data, it can express the functionality or the objective that the data scientist has. So the tool chain for software 2.0 is all of the surrounding infrastructure that allows for supervision and labeling of data to happen more readily. And it's the management of this supervision and this labeled data. And so the concern eventually in machine learning is going to become, how do you get your labeled data? Because the skeletons and the optimizers that you have are going to be powerful programs that only require data, and they can optimize themselves for the objective that you have. So in our implementation of cognitive-assisted interactive labeling, we have built on this idea of stochastic neighborhood embedding as an algorithm that expresses the requirements that we have. So we need to visualize our feature space, which expresses the quality of our features. And we need to be able to have the data scientist edit the feature space by defining constraints or labeling the data effectively. And then we need to have this algorithm integrate the data as you go along. So just need to maximize this so that you can see this GIF. So we have used a semi-supervised version of stochastic neighborhood embedding. And you can see here, as we apply supervision, we can see that these clusters contract together. And that is an effect that we would want to utilize. Just another example. So we have implemented this into the TensorBoard projector environment, which is part of TensorFlow. And you can feed a data set where you can effectively, by the initial homogeneity provided to you by stochastic neighborhood embedding, you can select a homogeneous cluster through one action and be able to apply labels in a compound fashion. So as you can see in this illustration, through very few actions, you can very rapidly annotate a data set. And every time that you perform an annotation action, this continuous calculation that is being done by semi-supervised stochastic neighborhood embedding utilizes that information, and it clarifies the feature space that we have. And one can see now how we have built up to this illustration that we have here for the radio astronomy data. Here we have an actual labeling session that has happened of the spectrogram. So one thing to note is that each one of these samples have to have a graphical depiction so that the human can very rapidly assess the homogeneity of clusters so as to select the best labeling prospects. So one can see the progression of this, this labeling process for very real-world, very messy data. You're able to rapidly label this data set, which before was an insurmountable, very difficult task to do, especially if you had to label according to the default of one action per label, which is very expensive to do. So this is the last slide I want to show you. I think I've run out of time. So this is a good impression of what this algorithm is able to do, and this has now been implemented into the official repository for TensorBoard, so everybody has access to this tool. So this tool is available to everybody, so you can ingest a real-world data set, and you can immediately start to benefit from this cognitive assistance to label very messy, very real-world data. So I think I'm going to stop there for any questions that you might have.
Thank you so much, Francois, for the amazing talk. And you did get to the end. Are there any? Oh yes, we do have some questions. For the use case, what was the accuracy of the labeling?
So, so that is the difficulty with the radio astronomy spectrogram data that we have here. We did not actually evaluate the accuracy because we had no ground truth to begin with. So one of the other difficulties is that there is no established list of RFI classes. So you might even have two experts disagreeing on what a characteristic class for a specific type of RFI should be. And so that subjectiveness of this particular real-world data adds difficulty to the situation, but we have not actually measured, except for the visual qualitative measure that we have confirmed in this visual process that we have here.
Thank you. Any other questions? What are you going to? Oh, can you comment on open source? How much of the code is open source?
So all of the code is open source. There are a couple of pull requests that have yet to be executed that allow you to have more fine-grained interaction in this environment. For example, to deselect more easily certain samples. So you might have a mostly homogeneous cluster selection where one or two of the samples do not belong. And so in some of the existing outstanding pull requests, we have made it more efficient to be able to do very fine-grained selection actions in this environment. But for the most part, it is open source.
Do you have a URL for people to find it?
So, if you Google TensorBoard, it's going to lead you to the GitHub page for TensorBoard, where you will be able to find instructions on how to implement it. And I believe that this is a Python package, so one can just pip install TensorFlow-TensorBoard, I believe. So this is readily available.
Right, so look for TensorBoard. I'm putting that in the chat as well to locate the code. And please thank Francois in the chat for his great talk, if you enjoyed it.
Thank you very much. Just one last point. So we're actually busy trying to see what this tool can do in medical data. So we're looking, for example, at the classification of blood cells and skin lesions in order to ease the process of being able to classify melanoma, as one example. So here we have a screenshot where we're trying to improve the tool to work better with more complex data sets where it's more difficult to distinguish between certain classes. So we're continuing our efforts in this space, and we think it's going to be a big part of the future of machine learning, in line with Software 2.0 and the direction of machine learning overall. But thank you so much for the opportunity. Thank you for watching. And if anybody have any extra questions, you can email me. And thank you. Thank you.
Francois, I actually muted you for a few minutes at the beginning of the talk by mistake, where you introduced yourself. So maybe just for the recording, you may want to, that bit wasn't recorded. So maybe you want to do that again.
Okay, yes. Hi, so my name is Francois Luus. I'm part of Alien Research Africa. I work in the South Africa lab, and we have some projects in radio astronomy. I'm trying to help the Square Kilometre Array South Africa to leverage machine learning for very difficult radio astronomy problems.
Great. Thank you very much, Francois. Any more questions? Any more questions before we close? Any more thank yous? Just please put your thank yous in the chat. And that was a wonderful talk, Francois. Very inspiring with the Software 2.0 as well. And you managed to complete in time. So thank you.
Yeah, I had to rush a little bit in the end, but I think we covered most of the material.
Yes, yes. Thank you so much. I'll leave the chat open for a few more minutes, just in case anyone has any more questions, but I'll stop recording now.
Thank you.